of more interest to your work than Oumuamua and aliens is the question of whether or not there are any objects of interstellar origin that have taken up permanent residence in our solar system. So first, I thought I came across a word that I liked, since we've been enjoying some words while we've been talking. And I thought I might ask what the term of art planetesimal, and then I also later encountered satellitesimal, which is another nice word. We'll get to some satellitesimals later, but what is a planetesimal?
So the planetesimal is the building block of the planet, right? The way the planet formation process unfolds is you start out with dust, right? In fact, you start out with a cloud that encircles the young sun, which has mostly hydrogen and helium, right? 99% hydrogen and helium and 1% dust. And all of that dust at first kind of sticks to other dust through effectively electronic forces. This is like not too different from how, if you don't clean under your bed and you have a hardwood floor, the air currents will kind of make dust bunnies in your, under the bed. But even if you were to wait for a really, really long time, a dust bunny is not going to become a planet on its own. And the reason is that process of creating larger and larger particles just by sticking has a natural fragmentation limit to it. Once these things grow to kind of a size of a centimeter or greater, then their mutual collisions destroy them. And so in order to grow from sort of 1 centimeter dust bunnies or millimeter dust bunnies to an asteroid, you need a different process. And that different process turns out to be that within this disk of hydrogen and helium gas, dust accumulates in clouds. And these clouds grow so massive that they collapse under their own weight to form effectively asteroids, and those are the planetesimals. From there, the asteroids collide and grow the planets, and that's how the Earth formed. But planetesimal is the building block, and satellitesimal, by analogy, is the building block of satellites. Some work that I've done, in the last few years, focuses on the formation of the moons of Jupiter and Saturn. And that's a really, really fun and interesting problem. But one of the coolest things I'll say about a satellitesimal is that if you type in satellitesimal into like a Word document, it will autocorrect to satellite animal. Okay, which I was so tempted to just keep, satellite animals in all of the, in my entire paper, because it just reads so much better than satellitesimal.
Yeah, I mean, we don't even need to get into satellitesimals now, because you're right, satellite animals is cooler. Maybe we should just talk about what those might be. But one more context-setting question before we talk about the potential of interstellar immigrants is, I don't think that, my audience they're not all astronomers. And I don't think people will realize that the solar system is much more than just the sun, our planets, our 8 planets, and then the ninth planet that your colleague Mike Brown killed, Pluto. And we'll get to the potential new planet 9 later. But so how big is the solar system? What do you consider part of it? And what are its most peripheral constituents? How far are they?
Yeah, I think it helps to think logarithmically when you consider sort of the scales of the solar system, right? And so, there's this exhibit, I think, in Toronto, where you can kind of walk down the street and kind of visit the different planets to get a sense of how far things are. But if you adopt the orbit of the Earth as a unit, which is often referred to as the astronomical unit, right, then the inner 4 planets, Mercury, Venus, Earth, and Mars, occupy a region that's kind of compact, right? Mercury is at 0.4 of the Earth-Sun distance, like Venus is at 0.7, Earth is obviously at 1, Mars is at 1.6. So you can kind of imagine them being pretty tightly packed. And then you have to kind of think in terms of the next order of magnitude when you consider the outer solar system, because Jupiter, Saturn, Uranus, and Neptune, the giants of the solar system, are at 5, 10, 20, and 30 astronomical units respectively. Okay, so when you really look at the outer planets, the inner planets look like this tiny conglomeration of little orbs, right? They're really close together. But even the outer solar system is nowhere near the end of the gravitational domain that the sun occupies, right? Going out another order of magnitude to say, 100, 300, all the way to 1,000 astronomical units, that's the domain occupied by what we now call the Kuiper belt, a field of icy debris that flowed beyond Neptune on very kind of elliptical, kind of skinny orbits. And as we go yet another factor of 10 further out to say 10, 20, 50,000 astronomical units, that's where we start to encounter the Oort cloud. Okay, and the Oort cloud is yet a distinct population, kind of quasi-spherical population of icy asteroids, which are so far away from the sun that they are not only affected by the gravity of the sun itself, but also by the gravity of the galaxy as a whole. And so their dynamics, how their orbits evolve over billions of years, is controlled both by their orbits around the sun itself, as well as the gravity of what we call the galactic tide. In fact, the long period comets that we see that come in from the Oort cloud, the key line of evidence that we have that the Oort cloud indeed really exists, all do so because their orbits get modified by the gravitational pull of the galaxy. And by the time we're sort of at a couple 100,000 times the Earth-Sun distance, that's when we really start to flirt already with no longer being bound to the sun. So there's a whole lot of real estate.
Mm-hmm. One just quick question about that. So the KBOs, which the Kuiper belt objects, you said have these elliptical, very skinny, sort of elongated orbits. The Oort cloud, those objects, since they're not just affected by the sun, but also, as I think you referred to it as the galactic tide, do they have a similar sort of orbit, or is it much different, or does it vary?
It's a whole combination. So they, by virtue of being affected by galactic tide, right, their orbits are ever changing. I mean, they're changing slowly, but by the dynamics with the galactic tide, they change their ellipticity. The ones that we see are the most highly eccentric, most highly kind of elliptical orbits of them, because, well, in order to see them, they have to come close to the sun so that we see the coma light up. So we kind of have a strong bias towards only seeing the tail that is the most highly eccentric. But yeah, if you kind of imagine what the Oort cloud looks like in physical space, it looks like a spaghetti of orbits, right? And not on a plate. It looks like a spaghetti inside of a washing machine.